Welcome to Pre-Calculus. Today we will investigate writing and graphing radical inverse functions, focusing on algebraic techniques to create an inverse and graphical strategies to confirm that a pair of functions are in fact inverses of one another. We'll take a look at two examples of writing the inverses of radical functions. Our first example here is g of x equals the fifth root of negative x over 2. So we'll begin by decluttering that g of x, and we're going to call that y. So that's how we'll start here. I'm going to rewrite this function as y equals the fifth root of negative x divided by 2. And the reason we want to declutter the equation is because to make the inverse, I'm going to switch my domain and my range, which are my x and my y. So to make the inverse, we'll make that change. I'll rewrite the equation as x instead of y equals the fifth root of negative y divided by 2. And once I've made that swap, I have in fact created the inverse. What I need to do now is solve for y so that it's in a graphable form. So that's what I need to solve for, circled there in red. So we'll begin by canceling this fifth root that's over the fraction negative y over 2. And to do that, I'm going to apply the power of 5. That will cancel with the fifth root. I'll also raise x on the far left to the power of 5. So my next step will look like x to the power of 5 equals now just the fraction negative y divided by 2. At this time, I keep solving for y. I see I have two things to reckon with. I need to reckon with the negative sign and the 2. And I can accomplish both by multiplying by negative 2. So the negative times the negative will result in a positive. And then 2 divided by 2 will cancel to give 1. I'll also multiply the left side by negative 2. And that will give me this function, negative 2x to the power of 5 equals y. I can switch that around, and that is now in recognizable graphable form. To indicate that this is the inverse of g of x, I'll put that function notation, the inverse of g of x equals negative 2x to the power of 5. And I will box that as the equation of my inverse. So the first step we've completed, we've written the inverse using an algebraic strategy. We switched x and y, and then we solved for y. So now we want to graph both the inverse and the original. So I'm going to create room for some tables. And we'll make two tables here. The left one will be for the original, so we'll put x. And I'm going to put negative 2 through positive 2. I don't know if that's a good interval of the domain to choose, but it is a good starting point. And there we're going to calculate the original g of x. In the second table, we'll also use same x values, negative 2, negative 1, 0, 1, and 2. And there we will be calculating the inverse of g of x. So to facilitate with making those outputs from our two tables, we're going to employ the use of Desmos. So we'll head over there right now. And I want to put in our two equations. So for the first one, g of x equals the fifth root. So I'm going to grab the nth root function from the keypad, the functions menu, and then miscellaneous. The nth root is right there, 2 above sigma. Lets me type in my own index. That's a 5, fifth root. And then under the radical is the fraction negative x divided by 2. And that gives me the graph there. So it looks like it's got its point of inflection there at the origin. I'm going to create a table. And I can see those points showing up on my graph, and it turns out those domain values are just right. Catches the function right around its inflection point. So we've got -2 output of 1, -1 output of 0.87, the origin. And then you can see that odd symmetry. 1 has the same value as -1 except flipped sign, -0.87. Same for 2. 2 has the value of -1. So I'll write that down. I do also want to calculate the outputs for my inverse. So that we'll call h of x equals -2x to the power of 5. Same as we did for our original function, I want a table for the inverse. And definitely I can record those values. Output for -2 is 64, ungraphable, but I'll record it. 3 middle points are very graphable. So -1, 2, 0, 0, 1, and -2. And then I also have 2, -64. Again, ungraphable. It's off my screen, but I'll go ahead and record it. So with those tables written down, I'm going to head back to the notes screen to reproduce them there. So just to remind, it was -2, 1, -1.87, the origin. And then watch the symmetry, shows that clear odd symmetry where these values are the same numbers but opposite signs. Let's put our values for the inverse. So it's +64 to the origin, -2, -64. Same pattern here, shows that odd symmetry. Let's graph these two functions. So in red, we'll graph the original. So -2, 1. -1 is +0.87, 0, 0. +1's -0.87, and +2 is -1. So we'll graph that function. There's our original graph. We'll label it as g of x. And then we'll graph our inverse here in the green. So again, -264 is off my graph, but I can graph -1, +2, 0, 0, 1, -2, and then again 2, -64 off the graph. Let's sketch this inverse graph. So we've got a rough sketch there. Let's label that as the inverse of g of x. Just to check graphically whether these look like good inverses, I'm going to plot the identity line. So this goes through the origin and has a slope of 1. Same as I go down into quadrant 3. That's the identity, y equals x. And I want to check 2 key traits on that line. So remember, if my inverses intersect each other, they should intersect on the identity. And I see that trait here definitely intersects on the identity. The second key trait that we're looking for pairs of inverses is reflection over the identity. So if I took the original and reflected it over the identity, this red graph would lie directly on top of that green graph. Same thing down below. If I reflected the inverse across the identity, its green branch there would land directly on the red branch. So we see also that it's symmetric across the identity. And that completes our task here. We've written the inverse algebraically. We graphed the original and the inverse and confirmed that they are a good pair of inverses with 2 hallmark features: intersection on the identity and symmetry across the identity. Let's take a look at one more example. So this one is a cube root function and a little different in terms of the algebraic placement of the cube root. So look and see that it's within a fraction. And let's see how that changes our inverse writing. So I'm going to zoom out to full percent. And let's start again. So I want to create the inverse. Remember, I'm going to replace f of x with y to reduce the clutter. And once I do that, I'm preparing to switch the domain and the range. And in an equation, remember that's switching x and y. So for my inverse, the way that I'll record that, instead of y, I'll write x equals, in the numerator, 4 minus the cube root of 4y instead of x over 2. And then just as we had seen in our first example, we want to solve now for y. I've got quite a few things to reconcile on the right. So what I would start with is this denominator of 2. So I need to make sure that's a minus sign up above. I'm going to cancel the denominator of 2 by multiplying the right side by positive 2. 2 divided by 2 is 1. I'll record that on the left. That time I've got now 2x equals simply 4 minus the cube root of 4y. At this time I want to move that constant 4 by subtraction. Cancels on the right side, shows up on the left. So now I've got 2x minus 4 equals negative cube root of 4y. I do want to cancel that negative, so I'm going to multiply this right side by negative 1. Negative times a negative becomes a positive, and I'm going to also represent that multiplication on the left. Let's distribute that through. That distribution is going to go to both terms, so really it will just flip the signs. This becomes negative 2x plus 4 equals now the cube root of 4y. Not much to reconcile now on the right side. Let's deal with that cube root. I want to cancel it, so I'm going to raise it to the power of 3. The cube cancels the cube root, and on the left, that cube goes around the whole term, negative 2x plus 4. I need to put parentheses there. The only piece left to move is this coefficient of 4. So what's left on the right side is 4y. To cancel the 4, I'm going to divide by 4. Divide by 4. And that gives me my inverse in graphable form. Let's record it. Y. So I'm going to rotate y around to the left equals, in the numerator, negative 2x plus 4 quantity cubed, all divided by 4. And to indicate that that's the inverse of f of x, I'll just put that notation. The inverse of f of x equals negative 2x plus 4 cubed divided by 4. And that completes the inverse writing. So we're ready to graph. Let's create our two tables. So remember, those left columns are x columns. We'll use our same 5, negative 2, negative 1, 0, 1, and 2. So I am putting both the original and the inverse on the same plane. Again, that'll help us to see, do they show the two characteristic traits of inverses? So we're ready to get our coordinates. We'll head to Desmos to do so. Once we get there, we'll clear out our previous work and enter afresh. So here in entry line 1, let's put f of x, this is the original function's equation, equals the fraction 4 minus cube root. So again, I'm going to select that from the function tab miscellaneous, the nth root, and I'm going to put the index 3. Under the cube root is 4x, and in the denominator is 2. So we'll graph that. So it's similar to our last radical function, but this one's been shifted up 2 from the origin. Here's our inverse. We'll call it g of x just to distinguish it from f of x. So this is also a fraction. In my numerator within parentheses is negative 2x plus 4, all raised to the power of 3 over 4. And that's shown up there in the purple. Let's get a table for these so that we can graph them on our work. So there, the table's generated for negative 2, we have the value of 3. Negative 1 is 2.79. 0 is 2. That's that upshift of 2. That's the y-intercept. 1 is at 1.21 and 2 is at 1. Let's get a table for that inverse. So that one, the first few points are very ungraphable. Negative 128. Negative 2 yields 128. That's way off my graph. Negative 1 yields 54, also way off the graph. 0, 16 is getting closer. I can graph 1, 2, and 2, 0. If I were to include some other values, 3, negative 2 would be a good one to include. So remember, you can always add to your domain list. That's the values we get to choose. Let's take those two tables. I've recorded them, and let's go back to finish our graphs. We'll fill in our tables here. So for the original f of x, we've got negative 2, 3, negative 1, 2.80, 0, 2, 1, 1.21, and 2, 1. For the inverse, negative 2 is 128, negative 1 is 54, 0 is 16, so the y-intercept is off the graph, 1, 2, and 2, 0. And then we did incorporate another point here, so let's write it in. 3 we included, and its value, its output is negative 2. Make sure we keep that in our blue color. Just to note that this is looking inverse in the table. Remember, if I've got a pair of points like negative 2, 3, in the inverse, it should show up inverted. And I see that here as 3, negative 2 in the inverse table. Do we have any others? Yes, we do. We also have 0, 2 inverted as 2, 0. So you can see that switching of the domain and the range in the equation. You see it in the table as well. And we even have a third here. 2, 1 shows up as 1, 2. So you can see the inverse relationship in the tables as well as the equations. Let's graph it, see if we see it there as well. So negative 2, 3. There in quadrant 2, negative 1, 2.8, 0, 2, that's got to be our point of inflection, 1, 1.21, and then 2 is at 1. So we'll graph in the original, and you can see how the cube root is a flat graph compared to the cubic function. Let's graph the cubic one. The cubic is more vertical. But again, that highlights the relationship between two inverses. 1, 2 is the first point we can graph. 2, 0, 3, negative 2. And my values at 0 and probably 4 is negative 16. So I'm going to just sketch in here, leaving these descending parts kind of hidden. It's not hitting the y-axis yet. All right, so that gives us, well, let me resketch there. I'm seeing that it's not gonna fit the bill. Sometimes starting at the inflection point helps. I think that's better. So we'll label these the way that we've got them color-coded. This is the inverse of f of x. The red is the original f of x. And then in the purple, let's put the identity line. Recall that that starts at the origin and goes at a slope of 1 into quadrant 1. And then we can complete the part there in quadrant 3 as well. So it's showing very clearly the intersection on the identity. Remember, that's one of the hallmarks on the graph that we're checking. Intersection on identity line. The other feature that we're looking to see is, do I see the reflection across the identity? So there I see that if I folded the original red f of x over the identity, it would land on top of the blue curve, which is the inverse. Same here, if I folded the inverse over the identity, it would land directly on the original. Thank you for joining for this investigation of writing and graphing inverse pairs. I look forward to seeing you next time. Until then, bye for now.